So now we're going to talk about theoretical evaluation. So remember, big O, there's two things that we need to keep in mind. The first being, we do not care about coefficients. And we will abbreviate that as coef. And the second thing is, we only care about the highest power. Right? So now let's look at some examples of this and how we might be able to evaluate this. So let's say we have a vector and let's put some values in here. We'll go 5, 3, 6, 1, and 8. And for our first algorithm, we want to find the largest number. The largest number, right? So you look at this and you say, okay, well that's pretty easy to do. All we need is a simple for loop, for x in the vector. Find the highest. And that we can do that using a simple if statement, right? So for this iteration right here, this is going to be an iteration. We know that x is going to be the value in here, right? So that's how many times we're going to go through. And for x in vector, well, this is going to be the length of our vector. So this correlates to n for how many items we have, right? And so by doing this find the highest logic down here inside of this iteration, we can logically conclude, since we're only having to iterate through the vector one time, that our big O notation is going to be O of n. And why is it O of n? Because we're only going through the vector one time, right? So now let's look at a slightly different example. Let's say we want to sort the vector, right? So for this, we'll do another for loop, and we'll say for I equals 0, I is less than or equal to n plus 1, I plus plus, right? So that right here alone, again, is the same as above, and that is O of n. Well, for us to sort it, we need to be able to compare and swap values in here. So we need to have our index here for I, and then we're also going to need another for loop, and we'll say it is j, and we'll start j at 1, right? Because we want to be able to compare I and j. So then we'll say j is less than or equal to n, j plus plus, and we'll say our big O notation here, let me clean that up, is O of n as well. And these are nested, right? Because we have O of n here, and then we have another for loop below it, which is also being executed every time that this for loop gets ran right here. So we have our nested for loops. We do our compare and swaps to sort the vector out. And with this being a for loop, and then we have our open bracket, and then we have our other for loop right here, and let's label these, bracket A, bracket B. Well, we close bracket B here, and then we close bracket A there. And what happens with this is that for every iteration in this A for loop, we're going to iterate through this loop as well, right? So I just want to make that really clear. And with that, we're going to iterate in twice, right? And with that means that we're going to have an exponent of 2. Or our highest power, yes, is 2. So our big O notation for this would be quadratic, as we showed in the experimental. And then our one up here, this is linear. So obviously O of n is more performant than O of n squared. And then if for some reason we had another for loop, so if we added another nested loop, for loop, well, now our big O notation would be O of n cubed, right? So hopefully that makes sense, because theoretical is a lot more time considerate when you're trying to evaluate your algorithm. And I wanted to talk about big O notation early on in this course as the first thing, because as we go through and look at all these different algorithms and data structures, I want you to be familiar with what the big O notation of that algorithm or data structure could be. And I want you to try and compute the big O notations for some of these algorithms and data structures as we go through this course, so that you're able to evaluate their performance, and maybe you can even enhance them to improve their space and time complexity. So it's really important that we really understand what big O notation is. So if you have any questions about it, please ask them in the Q&A section before continuing on in this course, because I really want it to be clear as to how you can compute the big O notation of an algorithm.